Okay, so I chose this title partly to imply something perhaps problematic about the story of resonant relaxation, at least as it unfolded over a landscape of a very rich landscape of collisionless instabilities, which appear to make the life of stellar systems around black holes somewhat problematic. This work is some work that will largely review other people's work as well, which I thought was the intention of a review talk. And plus talk about my contributions in collaboration with Sridhar, Scott, Stefan at IAP, and former student and colleague Meher Kazanjian, who's currently at Leiden. It's work that's been interpolating between physics department at AUB, the Raman Research Institute, the Institute for Astrophysics, and the IIS. I haven't had the chance to visit Leiden extensively, but hope to soon. It also is work that interpolates between these beautiful paradigmatic systems of galactic nuclei, though they come with some sort of caveat, which I have learned painfully having worked in solar system dynamics for a long time. We had one system around which we built our favorite theories, and our favorite theories faced dramatic revolutionary changes in relationship to extrasolar systems. Here we have two, and these two come as dual of each other, one being observed from the outside and showing really a beautiful, well-established, long-range equilibrium, a global structure, surely hiding a lot of complex details which are inaccessible to our current instruments, while we have a system, which is our galactic center, really hitting us with monstrously complicated dynamics, perhaps all transient and hence not particularly interesting from my point of view, though for observers I'm sure very important. At the same time that it actually hides very carefully the long-range features which M31 happily shares with us. So whether these two systems have anything to do with each other, I certainly have a crosstalk between these two channels. Now I will use the word channel frequently, having been bombarded with what an order of magnitude of channels for binary mergers yesterday. So this is a channel between M31 and the galactic nucleus, which has been very informative in my thinking. And the kind of questions we like to ask, at least the way I like to look at the problem, the way my friends like to look at the problem, is ultimately what determines these global features. If we see them, okay, what characterizes them? Are they equilibria? Are they subject to instabilities? Do these instabilities unfold over time scales that are interesting from an observational point of view? Are they instabilities that lead us to states that are close to what one would associate with the thermal equilibrium of that system? What are these thermal equilibria like? This is a fundamental question in the statistical mechanics of systems with long-range interactions. And I would like to think that the black hole came to rescue gravity from itself, or from our ways of thinking about it, by imposing a sphere of influence in which it controls the dynamics and actually regularizes the problem of statistical mechanics for long-range systems within the sphere of influence of that black hole. So we have a beautiful system to ask all sorts of questions. The most important for us here have to do with the route to thermal equilibria. Is this a route that is going to be naturally controlled by relaxation processes? Are collisionless instabilities going to be faced on the way and dramatically perturb the system, taking it to another equilibrium? Or are systems actually going to be subject to continuous stochastic forcing from their environment, which renders the resonant relaxation timescales for some systems far too long to be of any relevance in comparison to the collisionless relaxation timescales, which seem to take the system from one equilibrium to another? Plus, a very important issue, which is that in the course of relaxation, of course, we have the transient states, and as Benchi was implying yesterday in the study of the galactic nucleus, perhaps the S-stars and the warp that they experience is a consequence of a transient state associated with a recent event of star formation, a few million years old, and this is the time that it takes to actually disturb this population. But in addition to that, we may encounter metastable states in which the systems in an instability would get locked into a configuration that had very little to do with the thermal state, which we calculate from first principles. So a number of questions. And in thinking about these questions, at least when it comes to the thermodynamic end of the problem, the statistical mechanical end of the problem, the kinetic end of the problem, the foundational work in this field is that of Rauch and Tremaine, which essentially go back to an ad hoc description of relaxation in a system, a resonantly relaxing system, associated in this case with a Keplerian potential. So the resonance here is essentially the equality of radial and azimuthal motion, which renders a Keplerian orbit somewhat degenerate, and hence allows two Keplerian orbits to talk to each other much longer than they would talk to each other if they were just whizzing by each other in the field. They have a longer period of time over which to talk, and that time scale is controlled by the precessional time scale, which is that of the mean field in which these particles live. So if you allow for longer interaction, you should expect larger fluctuations of the two-body nature, and this is what this theory is trying to capture. So Scott's point of view and Rauch's point of view at the time, and by the way, the paper touched on all the fundamental questions associated with this process of astrophysical significance. So reading it even now, one can still find interesting open problems to pursue. So their point was, okay, we replace an orbital time scale with a secular time scale, which is now the pattern speed of the system, and we get a resonant relaxation time scale, which is on the order of n times that pattern speed. Okay, and that's reasonably fast in comparison to the two-body relaxation time scale, which now comes with the ratio of the mass of the black hole to that of the cluster times the resonant time scale. So with that picture, the field actually spent quite a bit of time, I would say 2 decades, trying to figure out how to make sense of this right-hand side of the Boltzmann equation. And having heard Pierre-Henri this morning describe the details of how these derivations take place, I feel justified in not saying anything about them. His lectures are so beautifully pedagogic, I can't better them, that's for sure. So you have the collisionless bit, you have the collisional bit of the equation, and you want to try to actually convey a physical sense of what goes in that term. And the community spent a lot of time after Rauch and Tremaine trying to make sense of that. In fact, Rauch and Tremaine gave us fits for what the diffusion coefficients would look like. And it took time to elaborate a series of exercises. And here I'm highlighting what I think of were sort of foundational developments on the path of this ad hoc and then eventually, you know, extreme numerical precision, which was achieved, let's say, with the work of Merritt, Alexander, Mikola, and Will. This is a beautiful numerical experiment, which is yet to be bettered in quality, though not necessarily in interpretation. That's another matter. So we have these works. In here, this is a generalization of the Fokker-Planck equation to allow for now a resonant relaxation diffusion term in addition to the two-body relaxation, and different levels of description of that source of diffusion, whether you model it, whether you fit it from numerical experiment, whether you make your models learning models, intelligent models, whether you make assumptions about the noise. All sorts of assumptions go into trying to improve the right-hand side. Okay? We're trying to improve the right-hand side. I would say that Madigan, Hopman, and Levin did a reasonably good job of trying to explain the emergence of a core within a cuspy central regions by solving actually the angular momentum energy contributions within the Fokker-Planck equation. On the statistical thermal end, I would say that Coxis and Tremaine actually started a line of thought that is now maturing into a full-fledged statistical mechanical description in the context of vector resonant relaxation. We did an interesting attempt at handling slightly less symmetric configuration in the sense that we allowed our orbits to be rather elongated, but we had to go through serious restrictions. I think this work by Bar-Or and Alexander came out of the blue and had a lot of promise, and I feel is going to start showing some of its consequences very soon. This is the way it went for a long time. And then we thought, OK, let's try to put this on more foundational terms. And I think the talk of Chavannes once again set the historical setting in which this development took place. And the development had two communities, the plasma community, the gravitational community. I come within a lineage of dynamical galactic dynamicists, partly due through my associations with, much smarter and established people like Scott or Sridhar. So I got to follow this lineage associated with the work of Gilbert, and then ultimately a very much ahead of its time piece of work, and not fully recognized work by Polyachenko and Shukman, which actually worked with action angle variables to try to understand the consequences of relaxation in systems allowing for a central mass. So this was a very early work. And then it led to this work of ours, a series of papers. If you're intrepid enough, you may try to go through them. I wouldn't make the attempt unless you're a postdoc and you want to try to solve some difficult problem and impress your advisor and your community. The point is that this exercise puts the field on solid foundations. Whether they're fully justified or not, there are still assumptions in that theory. It's a 1/n theory, and it relies on some level of orbit averaging. So within that theory, of course, there is the parallel development of Fouvry, Pichon, and Magorian, a very interesting development, and I'm hoping that this development will give complementary perspective on the resonant relaxation processes. And I understand that Fouvry and Baror are engaged actively into mining the implications of their tool set. So the Institute right now really is a hub of thinking about resonant relaxation. Whether it will relax on something useful or not remains to be seen. I'm excited, and I think that's enough. OK. Not my excitement, just excitement, period. OK, so just to give you an idea of what goes into that picture, I want to try to be fast through this. So ultimately, what we have is dynamics that lives in the sphere of influence of a black hole. The black hole imposes some level of regularity in its sphere of influence. This is a new thing. OK, this is a scale in the system, scale in a self-gravitating system, which is a problem in gravity generally, no screening in some sense. It's not exactly screening, but it actually contributes a level of regularity. So we have this hierarchy of time scale in the problem between the Keplerian orbital time scale, the secular, which is the pattern speed imposed by the self-gravity of a cluster, the resonant relaxation time scale, which is now a time scale that is inducing variations in the orientations and the elongations of orbits, all the while preserving their semi-major axes. So there is no energy diffusion in the problem, no kinetic Keplerian energy diffusion in the problem. The only thing that diffuses is the angular momentum. So in that picture, what one notices is that the Keplerian orbital time scale is the slowest time scale. So it behooves us, like it behooved many people before us in the context of planetary science, provided you avoid regions of orbit resonances, mean motion resonances. And it's an important issue, their role in inducing fluctuations in these systems. Something should be done about that. So we have a Keplerian orbital time scale, which is very slow. And so why not orbit average over that time scale, and proceed with Laplace, Lagrange, Gauss, and a whole generation of dynamicists to describe the motion of a star instead of a particle. And John showed us beautiful particles-based simulation of what happens in the galactic center. He will be very happy to see his galactic center evolve over a few precessional times within 3 days if we did it with ring-like simulations. And I'll be happy to provide our tools in support of his work. So the point here is that in addition to numerical ease, we take a star here. We know that it's moving around the central black hole on a Keplerian orbit. We take the mass of that particle and smooth it, swipe it, distribute it in a fashion such that there is more mass where the particle spends more time. In fact, you see it here. In some sense, now that we have Scott's model and all the series of work on it, what we have in M31 is a beautiful illustration of averaging at work. OK? This is luminosity at the apoapse, where things are most eccentric, where they're spending most of their time. This is where most matter is, and this is the beauty of that story. So when you do that, you enter into a new phase space. So you enter into a new geometry. The classical geometry, of course, is the parameterization of a Keplerian orbit by the Keplerian elements. That's fine. And so you have A, E, I, F is the angle on the orbit, G is the orientation of the orbit in the plane, and omega is the orientation of the plane itself. Now, when you do that, the proper thing to do, as Christoph pointed out, is to work with action angle variables. And the beauty of this system when it comes to Léonard, Balescu, Gilbert, you name it, formalism, we have our own channels also. So if you work it through, the difficulty is finding a suitable set of action angle variables with which to work, which is why our community has tended to stick to axisymmetric system, which is a big problem, in my opinion, as to how the field is going to evolve. Not a big formal problem, but it's a technical problem, and it has to be addressed. OK, so the cool thing about the Kepler problem is it provides us with a natural set of action angle variables. That's very nice. It's the dominant source in the system. That's very nice. The rest is perturbations. So from a perturbative point of view, all of stellar dynamics along galactic nuclei is a perturbation of Kepler. OK? This is even much better than in the solar system. OK? In the sense that mean motion resonances are difficult to come by unless you have a significant spectrum in the masses in the system, which we don't have. Now, the consequence of that is that, one, there is a reduction of complexity. You go from 6-dimensional phase space to a 4-dimensional phase space, in the sense that the action associated with the angle on the orbit, which is proportional to the square root of the semi-major axis, is now conserved. So now you have a set of integrals, a whole distribution of integrals of motion. And anybody who dealt with equilibria knows that this is a boon. It is a very useful thing to have as you build your equilibria. There is a reduction in the complexity in the sense that we went from 6 to 4 plus 1. Why 1? Because this one is a distribution which is invariant in the course of the evolution. And anybody who has done numerical simulations in these systems knows that the semi-major axis evolution is rather minimal. OK? Very little evolution. So we have a 4 plus 1 system. This is the dynamical equations. And these equations can translate into a Vlasov description of rings. So now I no longer want to follow particles. I want to follow distribution of rings in their appropriate phase space, which is action angle phase space of orbit averaged dynamics. And when you do that, you can reach the following conclusions. You have a collisionless theory for the evolution of clusters of stars around black holes, now of wires instead of particles. And in that theory, you have what is known as a Jeans theorem, which is a theorem that justifies the use of integrals of motions to build equilibria in these systems. So we have a very rich supply of equilibria. And John showed you how to build one lopsided equilibrium just half an hour ago. So we have a rich supply of equilibria, and they don't have to respect any particular symmetry. They are functions of the integrals of motion, which can involve angular momentum, energy, and certainly the distribution of semi-major axes, which is invariant in the problem. Now, in looking at these equilibria, you can then study stability. Our collisionless treatment, Sridhar and myself, provides solid foundations in which to examine results on stability, which have existed in the literature and have looked at an orbit average treatment only in a somewhat not direct fashion, I would say. Would you agree, Evgeny? Yes. So in this field, spherical equilibria were already examined. And we already learned that spherical systems, which have a monotonic distribution in the angular momentum, okay, which also translate in similarly monotonic distributions in the eccentricity, show stability. They are stable to the development of a lost cone. At most, as Scott showed in 2005, they can develop a neutral mode. Okay, I'll tell you more about that if you insist. On the other hand, what Yevgeny showed was if you have distributions that are non-monotonic in this same distribution, lost cone emptying of such systems, meaning removal of particles at high angular momentum, can induce large-scale instabilities. And this with the angular momentum, specific angular momentum of the orbits in your stellar cluster, scalar angular momentum. Yeah, isotropic system. Yeah. So non-monotonic distributions, which are sharply peaked, okay, hence deeply emptied lost cone, tend to be prone to instabilities involving L equal 3 type modes or higher. Okay, so this is a very interesting result. We also learned we could prove that axisymmetric razor-thin disks, so if you start with axisymmetric razor-thin disk and give a monotonic distribution of angular momentum in the disk, they are perfectly stable. If you introduce non-monotonicity, there has been indications building since about 2002, maybe earlier if you look at work in counter-rotating systems in galaxies, that counter-rotating flat systems are prone to secular instabilities, which may induce the formation of lopsided features over rather fast time scales. So a lopsided mode, which traps orbit, like Anne-Marie was showing, naturally arises in the course of these instabilities, shaping the phase space in the course of its evolution to capture enough stars to build its m=1 mode. So there is a number of results. Let me just finish this. So there is a number of results in relationship to counter-rotation. Tremaines gives a proof of this in the context of the collisionless Boltzmann equation. Polyachenko does a related treatment allowing for a loss cone. And here we have a numerical illustration of the process. Yes, Christoph? Yes, so in our setting, the use of secular is different from yours. So there is no diffusive evolution of the system in this case. Secular in the context of planetary dynamics, celestial mechanics, is the term one uses to describe dynamics in the orbit average limit. Okay, now having handled the collisionless bit, you move to the collisional bit. So you have a particle description, like Pierre-Henri showed us beautifully this morning, that accounts for the effects of fluctuations, two-body correlations in the system, and how they contribute to the diffusive evolution of the mean field. So you have a mean field equilibrium, and you have two-body fluctuations, and you don't want to spend your time following them. You want to follow their effective contribution to the evolution of the mean field. All right? So there is a number of treatments in the particle setting. The breakthrough for galactic nuclei was to realize that if you do it in ring systems, you get all the benefits that ring systems have shown historically over the last 400 years or so. And if you allow for that, you can develop analogs of the theories, whether coming from the line of plasma physics or coming from the line of self-gravitating systems. You can develop a beautiful treatment for the collisional evolutions of systems of rings, which is a mean, it is a continuum theory, and it is a 1/n theory, so it does an expansion in 1/n, but it follows the continuum evolution of the underlying mean field. Now, in that theory, what we learn is that interactions between populations of stars, like Christoph showed, that happen to have either resonances in the apse or resonances in the nodes, which will, in extreme cases, provide an explanation for scalar resonant relaxation or vector resonant relaxation if they're operating separately. In general, the phase space is rather mixed. The populations can be chaotic, exploring islands that involve oscillations in G as well and as omega. The separation is meaningless unless you impose external potentials such as cusps, like Benchy and Scott did, and actually enforce averaging over the apse and leave you with the node precession as the dominant sort of form of relaxation in the orientations of the orbits. If you do that, you get simplifications, but we're trying to get the least complex accurate theory. We're not trying to find our way to halfway solutions. So what we have is the least complex accurate theory with which to develop a complete treatment of resonant relaxation, and there is the equivalent and beautiful treatment by Fouvry, Pichon, and Magorian, and they have, I think, complementary things to say to the field, and I'm very excited to see how they will evolve. If you now insist that the wakes or the effect of a particle on its neighbors is now, I mean, the wake-wake interactions are negligible, i.e. the effect of a particle in the distribution, and then this effect on the effect of other particles is neglected, then you can end up with a situation in which you have a Fokker-Planck description for the dynamics, and you're back to a Fokker-Planck treatment. Only now you have closed form expressions for the diffusion coefficients that ad hoc developments have tried to approach over 20 years. Now, these closed form expressions are coming between quotes because they involve significant computations and levels of assumption. So let me go into, oh, I didn't want to flash equations. you already equationed out by now. Anyway, so this is what it looks like. Okay, this is what the equation looks like. Now this is the diffusion equation for F. This is our right-hand side. The right-hand side involves the usual dissipative and fluctuating term, and they're written in terms of a wake. The wake is the way that Gilbert's theory represents the two-body interactions in this system, and this wake picks up largest contributions from resonant populations of stars that are talking to each other through dynamical channels. So, and then you have the fluctuating part, which involves diffusive contributions. Okay, the key thing in any working tool set in this theory is one having an equilibrium, and the equilibrium is going to be characterized by a distribution function over the space of rings and by the associated potential. But more importantly, really from a technical point of view, it's having a ring-ring potential, which you can describe in some closed form fashion that would facilitate calculations in actual settings. And that ring-ring potential is the generalized form of the Poisson kernel when you average over the angular motion on the rings. Yes?
Can you clarify one thing?
Yeah.
So in the previous...
You want equations?
I'm sorry. So this is the left-hand side is it still for the other side?
This.
Is it still for the orbit average and then you include...
Yeah.
And then you include contributions in the right-hand side that
Yeah.
are not necessarily from orbit?
No. They are the orbit averaged contributions of the fluctuating component. That's the way you want to think about it. And they're operating over the orbit averaged equilibrium, which is assumed to be evolving in a quasi-equilibrium fashion in the course of this dynamics. So we're always close to an equilibrium whose action angle variables were used in order to characterize the effect of fluctuations on the system, which are captured by this complicated procedure. Yeah, sure. Okay, so this is key. This is key. This is the heart of the game. And if you have an access to that, and God knows Scott and I spent hours trying to get access to useful and meaningful forms of that, you can make a lot of progress, whether by solving the Fokker-Planck equation associated with the system or actually asking what is the maximum entropy state in these systems, which is a perfectly legitimate statistical mechanical questions in this field. Okay, so the ingredients, just to be specific. So you have to have a quasi-equilibrium. You need an explicit expression for the orbit averaged interaction potential. Okay, so we have a rich supply of these coming from a planetary dynamics. We have used the softened form of Laplace-Lagrange, which is relevant for hot stellar systems. There is a debate on what softening means. It's the eternal debate in the context of galactic dynamics. We introduced this rather singular form of logarithmic interactions for wires that have all shared the same semi-major axis. And then there is the very rich trail followed by Cox's and Tremaine by looking at the interactions of averaged planetary, Keplerian orbits. Okay, I talked about the apse and node resonances which feed into the wake. So one has to study where these resonance obtains. And Christoph gave an illustration of resonant interactions in his talk. So we have to locate them, and they have to be located in the context of the mean field, the precessional frequencies associated with the mean field. And keep in mind that that mean field is evolving in time. So the distribution of resonant locations will be evolving with time as well, to the point that they may actually quench the process altogether or actually drive it to a situation where an instability occurs. Okay, in parallel with this development, so the kinetic theoretic development was coupled to a development numerically, which says, now I have rings. I've looked at them from the point of view of collisionless Vlasov equation. I've looked at them from the point of view of Fokker-Planck equation. What about if I want to look at them from an n-body situation and go to an n-wire situation? Can I write codes for n-wires? And the answer is yes, and this is based on a generalization of a beautiful idea of Gauss of how to compute the force or the torques between orbit average wires, except that Gauss developed it for cold planetary systems. So orbits don't cross. They're very gentle, small eccentricity, widely separated. Everything is fine. You try to push that on a stellar system, like Rauch and Tremaine did with an early version, and you run into trouble. So what we realized is that Gauss's idea is actually softenable. Okay, so you take softening, and it pushes through very nicely, and the idea works out beautifully. What we have learned recently in work with Meher, who is at Leiden University, is that this algorithm is eminently parallelizable, and it allows you to evolve a few K rings for billions of years, something that would require an actual particle simulation orders of magnitude more effort to complete within the month period that we are interested in. So we cover secular dynamics, relaxation included, over secular time scales. So this is perfectly matched with secular theory. The theory is modeled with the appropriate numerics. This is the complete numerics for the theory. What we have now is billion-year simulations for clusters, which correspond to about 10 resonant relaxation time scales of 5K wire clusters. This is all the computing time we have so far, and we're looking for 10 to the 7 supercomputing hours. The computation were done on Surf Sarah in in Holland. So this is the supercomputing facility. And we've certainly made use of the IAS cluster. Maybe it slows down some of your jobs. We're carrying out background calculations of clusters. We can allow for a loss cone. This is a technical issue that I haven't fully handled yet. We have a GR to arbitrary order. And since binaries is like the buzzword nowadays, yes, we can let your binaries come into our picture. Whatever binary, whatever channel, whatever evolutionary process you want, we can allow for it. And then you can have external perturbers. So you can have gas, you can have migrating clusters, and you can have binary black hole if it's sufficiently widely separated or interior to the cluster. All of that can be allowed in naturally into this description. The promise of that theory, of course, is to provide for efficient sculpting of eccentricity inclination distributions. Now, personally, I don't find that exciting. It's like you're excited about a cloud. Okay, I'm more interested in how hurricanes form, let's say. Okay, a cloud is useful. You can watch it. It passes. You can trace the cloud. It has a time scale. It rains. It evolves. It dissipates. If it is a transient, sorry? G2? Ah, that's true. That's true. I have to be careful. I have to be careful. Yeah, I didn't mean to be so witty. Sorry. Yes. No, I mean like what Benchy was showing, which was a very clear indication of the arising of the structure of the orbits in the interior as a transient state. You would agree with that? Transient, few million-year-old state. And the question is, how would it evolve? And what does it say about actually the structure of the system as a whole? It's interesting. It's very important to have a mechanism. But then it should compete with every other transient mechanism. And there are, I'm sure, plenty to go by since the realization of these young systems emerged. You can also ask questions about the black hole feeding rates. Okay, so we want to feed the black holes. And instabilities actually tend to drive feeding rates. This is increasingly realized. We had already realized it in looking at counter-rotating instabilities. They put things on radial orbits, whether you like it or not. And these radial orbits will want to interact with the central black hole. Then a very important question is the nature of dynamical friction in secular secular dynamical processes. And it has relevance for planetary systems as well as for galactic nuclei. And then binary mergers over relaxing orbits is a very important topic. And Cristobal convinced me that this is a very important issue to pursue. And so we're busy trying to pursue it. So the models, though, unfortunately have lagged behind, you know. Okay, but like Yuri was saying, there is some psychological impediment to running away from symmetry. Okay, that psychological impediment apparently I don't have. If something looks symmetric, I want to be away from it. Okay, so I want to disrupt any sense of symmetry. It comes perhaps from living in a troubled environment. So I have to see tumultuous situations arising. And anyway, I'm certainly not Platonic from a philosophical point of view. So I don't like symmetry, but apparently it's useful to actually make sense of what is happening. So friends in the community keep appealing to spherically symmetric, axisymmetric. And you know, even if you allow for spherical symmetry or axisymmetry, you can find a way to preserve some form of spherical symmetry while allowing for the axisymmetric slow contribution on top of it. You know, we try our best. All right? So we go for symmetric, axisymmetric, which is a dangerous, if natural, assumption for some. Okay, it's a very dangerous assumption. In particular, I mean, it's questionable how things came to be spherically symmetric in the first place. So one has to keep in mind, though, this notion that spherical clusters can be loss cone unstables, and we want things to have a loss cone, and the loss cone is generally emptied, and we worry about how to fill it. And you worry about how to fill it, maintaining the same structure, which is supposed to go unstable as you empty it. So that's a very interesting conundrum. And this is the kind of picture that arises within this framework, where you take a spherical cluster, you look at the cusp in that cluster, you impose a form of diffusive behavior associated with resonant relaxation, and you try to form cores over interesting time scales within clusters, not wondering whether chord clusters actually can go unstable or not, hence undermining the whole spherical symmetry assumption that you have used to build your theory. Okay, that's a bit problematic. So for me, symmetry is almost the art of solving what is solvable and then trying to convince observers that this is a useful thing. Okay, so this is useful within an economy of grants and asking for computing time, jobs, etc. It's not useful for me from the point of view of actually building useful pictures. Symmetry is more often than not broken in the course of secular instabilities, which appear natural, violent, and relax over reasonable timescales. Symmetry is questionable even in the way things form. You tend to form things in disk, and then you want to warp them, and then we want to introduce very strange non-symmetric structures, and then you want to symmetrize them. So why start with symmetry? By now it should be clear that from my point of view, I start with symmetry in order to break it. Okay, so how do we break it? So we did a few thousand particle, thousand ring simulations carried over 1 billion years, which is about 10 resonant relaxation timescales. On the left here, what you have is a beautiful equilibrium. So this is a thermal equilibrium of the system. It's a trivial thermal equilibrium, but nonetheless, it is comforting to see that our algorithm actually preserves equilibria when you say that it is an equilibrium. It has a distribution of eccentricity, which is linear in the eccentricity, and the clusters are monoenergetic in the sense that all particles tend to have the same semi-major axis for computational ease at this point. Okay, so this is an equilibrium. Now, you take that same equilibrium and you introduce a loss cone at high eccentricity, and the distribution gets sculpted in a way which remains to be calculated from theoretical first principle arguments. You introduce a loss cone on a thermal equilibrium of this nature. How does the distribution of eccentricity evolve over time? Now, okay, this is, sorry for the blotches, they are not physical. Okay, so this is what you see if you look at the same distribution in a framework which is similar to what Anne-Marie showed. Namely, look at particles within lens vector space. Here, looking at the projected lens vector space. So it's initially isotropic. And then the distribution has a wide spread of inclinations. This is the inclination axis as expected from a isotropic spherical distribution. And then with loss of particles, it starts developing some interesting wobble, which develops into a full-fledged instability, the details of which I cannot fill you in the course of this discussion. But this is a form of secular instability that arises in the course of relaxation processes, which is neglected in every calculation of relaxation. Okay, so that's just a warning. Yes, I wanted to show this. Here is where we stand. This is where the numerics stand, and it can get much finer. And we're working. Yes. A loss cone at a certain radius. It's a capture radius. That's right. That's right. So particles are getting removed when their periapse gets within that sphere. That's right. So this is where we stand numerically. At least this is a beautiful calculation, what I think of as a beautiful calculation leading into the sculpting of a distribution in the context of resonant relaxation as well as self-consistent dynamical evolution. This is what it looks like. So this is an N-ring simulations which capture two-body interactions exactly. So the theory is trying to capture what this system is doing. So all the fluctuations are captured exactly within this, within the orbit average limit. Yeah. No, two-body interactions are captured in the numerics. I don't have to put them by hand. Yeah. No. This is not allowed. The time scale for that process is an order, maybe 2 orders of magnitude longer than what we're looking at. Yeah. And to the right here, I'm showing something that is fresh, hot out of the printer, work of Bar-Or and Fouvry, enterprising young fellows, putting shared machineries, right, complementary machineries to work in computing. I think we have here perhaps the first instance of scalar resonant relaxation computed in a model problem, albeit. Okay, we're taking a particle within a cusp allowed to evolve in the course of resonant relaxation. And what we're seeing is a relaxation profile or the diffusion coefficients associated with this dynamics computed within their formalism as compared to two-body relaxation. I put this here as an invitation for you to talk to these guys who, for some reason, were not allowed to talk as organizers. I personally wanted to hear them talk about this work, and perhaps we can organize something tomorrow around that. So this is very exciting, and I'm very excited to see these works talk to each other, and let's see how far we can go. OK, now, this slide I call Yevgeny's vision. Yes, this is Yevgeny's vision. So this is the result of secular stability work that Yevgeny Polyachenko, his departed father, and Shukman studied in 2007. So they studied the stability of spherical cluster with these high eccentricity regime, peaked high eccentricity regimes, which sort of coincide to the wish to have radially anisotropic distributions. Okay? So these radially anisotropic distributions, which have a central black hole, are prone to L=3 instability. And we studied them in the presence of a loss cone. So we start with something that is initially stable, and we let it evolve. And sure enough, we see the development of large-scale L=3 modes, as expected in Yevgeny's treatment. But we also see the growth of associated L=1 modes, which is likely stimulated by the L=3 structure. So this is where the subject stands. We have an explorations of instabilities, which is required because they seem to restructure the systems over collisionless timescales, which are quite fast in comparison to resonant timescales. We have all the machinery to study the question of collisionless relaxation, the outcomes, the timescale for relaxation, and the possibility of metastable states occurring on the way, which could obviate anything we calculate from a thermal equilibrium point of view. Now, resonant relaxation in systems that inherit the symmetry of equilibria. So this is related to studying resonant relaxation in lopsided configuration. This is not a fundamentally difficult problem, but it is technically more challenging because the action angle simplification of the Kepler problem is now lost as the mean field of the cluster now imposes its own phase space structure over which the dynamics has to be studied. And we have to look at competition between disruption of the systems and relaxation. If you thought I'm done with the talk, I'm not. Let me leave you with warnings. In fact, I still have a full half, but I leave it for drinks. Yes, I leave it for drinks. OK, so I leave you with warnings. OK, all of this was meant to suggest a series of warnings, OK, which is what a disruptive creature like myself tends to do. So resonant relaxation, perhaps, but you have to worry about the relaxation onto collisionless instability, onto saturated state, then it's resonant relaxation. Okay? So this is presumably what happened in something like M31. This is presumably what may be at work on larger scales in the galactic nucleus. I don't know what observers have to say on the larger scales. I'm waiting to see. They seem to be competing over whether there is a cusp or no cusp, how far the cusp extends from Germany to California, how deep does it go. These are very fundamental issues, and I hope we get resolved. There is the collisionless relaxation timescale, which is not constrained at all. Okay? So violent relaxation is a big word that was introduced about 40 years ago. It's violent. It should appeal to me, but it doesn't. Okay? It just doesn't work for me. Violent relaxation just doesn't work for me. It's like something for nothing, as far as I can tell. Our systems should offer a better descriptions of how collisionless equilibria arise, and I feel that we are in a position to say something about that. Even then, the time scales for the relaxation, okay, can be orders of magnitude shorter than RR time. This is the collisionless relaxation time. On the other hand, they could be order of magnitudes longer if you get caught into these metastable states. And the second half of the talk was to show you some of these metastable states. And then you have the most interesting thing as far as I'm concerned when it comes to doing astrophysics, is that everybody keeps telling us that these systems are subject to perturbations of various sorts. They ingest clusters, they go through starburst, and the timescales over which these things happen are interestingly related, though perhaps not for the galactic center where we have this transient feature that we are all busy trying to explain. Yes? So, but you get features happening on the order of 10 to the 7, 10 to the 8 years. You're ingesting clusters, you're perturbing the system, and yet you want to study it within the context of resonant relaxation in a completely isolated system, quiescent, evolving through equilibrium. I find this problematic. Okay, I find this problematic. And I think, the more I think about it, which is why my title was Whither, Resonant Relaxation, is perhaps that resonant relaxation is quite relevant, but it may be relevant for systems that are too transient or too difficult to observe. So in that sense, what we're observing could be the consequences of things that are happening over faster time scale. And resonant relaxation is operating, but things get disrupted over faster time scale, suggesting a sort of metaphor. I don't want to think of it physically, sort of a metaphor of relaxation oscillation, where you get pulses of perturbations, okay, and then you get a relaxation process happening over fast collisionless time scales, perhaps some collisional time scale in the evolution. Yes. Should I show you what I mean by the beauty of metastable states? Is there a, so let's go. I had a few slides related to Anne-Marie's work. I can do them privately over coffee. Okay, let me show you what things look like when you want to actually look at actual systems. So here what we have is a full distribution of rings now captured in a particle mesh code. And the particles are rings, okay? So it's a wire mesh code, which allows us to carry out resolution to arbitrary precision, done with the collaboration of my colleague and friend at the Institute for Astrophysics, Stéphane Colombi. This is the most stable and yet most extreme configuration. And let me explain what we have here. What we have here is the lens vector sphere. So on the south pole, you have counter-rotating orbits that have zero eccentricity. On the north pole, you have orbits that have prograde and have zero eccentricity. On the equator, you have a distribution of particles that are going in opposite directions, counter-rotating with nearly radial eccentricities. Now you ask, how do they survive the central body? It's a very important question, which we ignore here. This is a system which is meant to be stable. Okay? It is a monotonic in the language of that I described earlier, so it's meant to be stable, and this is what it looks like. The band evolves in a very stable fashion. This is, except for these fluctuations, which would be very interesting to capture from a resonant relaxation point of view. Now, you look at this system. This is now a counter-rotating system. So you get two counter-rotating populations that start at the pole with near zero eccentricity, and they go unstable. And they want to go to the equatorial region, and this is how they relax. So this is the process of collision-less relaxation, establishing an equilibrium, which ends up looking lopsided, perfectly lopsided in the density framework. Now, I think we can capture this stage. I think we have difficulty capturing this stage theoretically, okay, at this stage. Okay, this is what thermal equilibria would expect. Thermal equilibria would expect that things, as you decrease the energy on the particles, they would develop lopsidedness. Okay, the equilibria of these systems are naturally lopsided when there is little angular momentum to go by, and they develop increasing lopsidedness, which looks like that in distribution space. So these are lopsided features arising as perfect thermal equilibria of resonant relaxation processes. Now, when you actually do the calculations, you learn that equilibria are not reached in a always in a straightforward manner. Okay, things don't tend to linger across a whole family of equilibria and never really go very easily to the expected thermal equilibrium. This is familiar already from the context of systems with long-range interaction. We're just exploring it here in the context of our systems. And so this is what things look like. Now you take a prograde population. It's an annular region, so it corresponds to a range in angular momentum. It's expected to go unstable in this case. It is non-monotonic, so it's certainly not expected to be stable. And this is the fluid mechanics that unfolds over the phase space of this system. This is how the instability develops. If it looks reminiscent of vortices, it's not surprising. The dynamics sort of collapses on vortex-like dynamics over spheres in an interesting way. So the system goes unstable. It develops granular structure, and that granular structures get sheared. The process here is collisionless. Perhaps this is what Lindenbell meant by violent relaxation. It seems fairly gentle to me. In fact, it evolves over time scales that are essentially adiabatic when as far as the particles are concerned. You can let this evolve, and it will evolve to a collisionless equilibrium nicely. On the other hand, here is a situation where the prograde population, which is 10 times more massive than the retrograde population, goes unstable. The retrograde population is also subject to a 5-fold instability. This system, which previously developed a 5-fold kind of Rossby wave-like pattern, is now developing a pattern which is stable for a very long period of time. In fact, we ran out of computing time trying to see how it will relax. So an equilibrium is developed, which is very far from the expected thermal or collisionless equilibrium, namely an equilibrium which has a lopsided feature, in which this system is caught into a metastable configuration. Now, try to capture this time scale in relationship to resonant relaxation time scale. You'll be way off. Now, these warnings already exist in the literature on long-range system. Metastability is a very important feature. We've already experienced it with numerical simulations of N-ring type behavior, and now we're seeing it at near collisionless limit. I'll stop here.